topic, methodology related to finding optimal paths. A student will be able to demonstrate various algorithms that find optimal paths. Here, instead of finding only a specific node, which is the goal node, we will try to find the optimal paths that lead us from the start to the particular goal. There are various algorithms that do this: the branch and bound, Astar, IDA star, divide and conquer approaches, and Beamstack Search. The branch and bound algorithm is very similar to backtracking in that a state space tree is used to solve a problem. It does not limit to any particular way of using the traversing of the tree, and it is used only for optimization problem. It computes a number which is called as a bound at the node and determines whether the node is a promising node, and therefore we have the number which is the bound on the value of the solution that could be obtained by expanding the state space tree beyond the current node. While implementing the branch and bound approach, there is no restriction on the type of the traversal that we are going to use. Backtracking is used, the nodes are reachable, and an essential element of the branch and bound is the greedy way in which we are going to estimate the value of the choosing one node over the other. This is called as a branch and bound heuristic. It is an underestimate for the minimal search and overestimate for the maximal search. And hence we go for pruning the promising nodes to get our solutions at a faster rate. The next algorithm that we will be using is the Astar algorithm, which is based upon the factor that we have f dash, a heuristic function that estimates the merit of each node we generate. This f dash is how far we are from the start to how far we are from the goal. How far we are from the start is based on the function which is g, and h dash is how far we are from the goal. So f dash represents an estimate of the cost getting from the initial node to the goal node state along the path that generates the current node. The basic lists used are open and closed. Open are having nodes that have been generated and have had a heuristic function applied to them, but which have not yet been examined. It is a priority queue in which the elements with the highest priority have promising value of the heuristic function. The closed is again a list which have nodes that have been already examined, and these nodes are to be kept in the memory. Where the new node is generated, we need to check if it was already generated before. The algorithm goes by starting with open containing the initial node only, and we start with the node's value to be 0 and h dash value of which it is, and its f dash value is now h dash plus g value is 0. So h dash plus 0 is h dash itself. So we set the close to the empty list. Now until the goal node is found, repeat the following. If no nodes are on open, report a failure. Otherwise pick a node on open with the closest f dash value. Call it as the best node. Remove it from the open, place it on closed if best node is the goal node, and if so, exit the reporting of a solution. Otherwise generate a successor best node and do not set the best node to the point to them yet. For each of the successor, do the following: set the successor to the point back to the best node. These backward links will make it possible to recover the path once a solution is found. Then we compute g of successor is g of the best node plus the cost of getting from the best node to the successor. We now see if the successor is same as any of the node in the open. If so, call it as an old node because it has already been there, and we can throw the successor and add old to the list of the best node successors. Now decide whether the old's parents link would be reset to a point to the best node, and it should be if the path is found between the successor which is cheaper than the current best path to the old. See whether it is the cheaper to get the old via its current parent or the successor via its best node by comparing the g values of the old is cheaper, then you do nothing. If the successor is cheaper, then reset the old's parent's link to point to the best node, record the cheaper path in the G old and update the F dash old. If the successor was not on open, and go to look whether it is on close, the already visited nodes. If so, call the node as the closed old and add old to the list of the best successors. Now follow 2C and set the parent's link of G and F dash values appropriately. If we have found a better path to old, then we propagate the improvement of the old successor and continue until the branch terminates with the node that is either still on open or has no successors. If successor was not on closed, then put it on open and add it to the list of best node successors and compute F dash now of the successor to be G of successor plus H dash of successor, the path that leads from the start to the current and current to the goal. Here we have interesting observations that G function could be chosen with the node to expand the next of the basis of how good the node would look like and how good the path to the node was by incorporating G into F dash. We will always choose our next node to expand the node that appears closest to the goal. If we care to get a solution somehow, now generate G to be 0 always. If we want to find the minimum step path, set the cost of going from the node to the successor constant. If you want to find the cheapest path and some operators cost more than the others, then we set the cost of going from one node to the other to reflect these costs. The role of H dash, taking you from the current node to the goal, is the perfect estimate of A star and will converge immediately to the goal with no search. The better H dash is, closer we will get to the directed approach, wherein the value of H dash is 0, the search will be controlled by G. The value of G is also 0, the search strategy will be random. If G is 1, search strategy will be a breadth first search. If we have guaranteed that H dash never overestimates H, and A star will find an optimal path to the goal. The next algorithm, IDA star, is similar to the iterative deepening depth first search, but with the following modification, where the depth first bound is considered, which modifies the F limit, and we start with the limit is equal to H of start. We prune the nodes. If this is greater than the F limit, then the next F limit is considered to be the minimum cost of any node that is already pruned. Iterative deepening is a kind of uninformed search strategy which combines the benefits of depth first search and breadth first search, and it has an advantage that is optimal, complete, and has a modest memory requirement. IDA star, which is iterative deepening of the A star search, is performed by the depth first search limited for this F bound. If the goal is okay, else increase the F bound and restart. How to establish this F bound? It's initially setting F bound to FFS and generate all the successors, record all the minimum successor is greater than the FSS which we have initially considered, and continue the minimal successor instead of FFS. IDA star is complete, optimally efficient, and does not require a priority queue for execution. The next method used is divide and conquer approach, which divides the problem into number of subproblems, conquer the subproblems, and combine the subproblems solutions that we have done in conquer to get a solution to the original problem. Note, often the conquer step is done recursively till we are satisfied with the result. The approach here used is to divide the problem into subproblems. Subproblems must be of same type. Subproblems do not need to overlap. Solve these subproblems recursively. Combine the solutions to give the original problem. The Beamstack Search is another algorithm which concentrates on having completeness at any time. Therefore, it is called as complete anytime algorithm. It has a complexity of O of D into W, which is associated with its memory. where D is the depth of the optimal solution, W is the beam width. And it uses the novel beam stack structure which stores the most promising unexpanded nodes at each level. It uses bounds which are admissible pruned and suboptimal nodes. It outperforms the various algorithms like depth first, branch and bound, the depth first iterative deepening Astar algorithm, and the breadth first approach, because it uses fringes in the size of its width and branches that are leading to W promising nodes at each level. The width bound reduces the complexity, and hence we have now a memory complexity of O of W into W, and it is incomplete due to the inadmissible pruning rule. The Beamstack Search makes some meaning, okay, when it builds off breadth first beam search, pruning layers of the beam width, each layer expanded to the most W nodes, expanding the layer of the Fn bounds, generating an estimate f of n which consists of g of n and h of n as in the Astar algorithm to see that h of n is admissible, and we have Beamstack Search stores this f of n ranges for each of the layer. The successor nodes have f of n value in the range, and we use backtracking pruned nodes by shifting f of n, which provides the completeness. For our references we have used. Thank you.